Radiation is dangerous. Uranium will kill you in mere moments. There is no safe level of radiation. We live in a radioactive world. Our bodies are bombarded by radiation from every direction, from our first cell divisions in the womb until our last dying breath, and probably afterwards. When we speak of nuclear radiation, we are talking about a form of radiation known as ionizing radiation, which has the power to change the molecular structure of objects it comes into contact with, such as our bodies. We will simply call this ionizing radiation for brevity. There are many sources of radiation. The universe bathes our world in cosmic radiation. This may be readily observed on an airplane. But space is not the only source of radiation. Holding a simple stone to a Geiger counter reveals the secret radioactive nature of our world. Natural soil, in fact the entire crust of the Earth, contains radioactive elements. On average, for every 1 metric ton of the Earth's crust, 6 grams of thorium, 1.8 grams of uranium, and 1.17 grams of the radioactive isotope potassium-40 can be found. These naturally occurring radioactive materials can be found in all of the soil of the world, from your potting soil to the sand on a beach. The naturally occurring radioactive material in our world finds its way into our bodies each day. The average human ingests approximately 474.5 micrograms of uranium each year. Our own bodies maintain a stockpile of potassium, which we need for our very lives, but also being slightly radioactive. Every second of your life, naturally radioactive potassium-40, an isotope of normal natural potassium, decays into argon-40 or calcium-40 within our bodies. The average adult human experiences approximately 3,700 nuclear decays per second from potassium-40 within our bodies. What does 3,700 decays per second sound like? Let's listen. Over time, some of this ingested naturally radioactive material may cause cancer, but the chances are very low. You cannot avoid this risk. Luckily, our bodies have evolved to handle these common levels of radiation. Our bodies, and those of all creatures on Earth, evolved in a sea of ionizing radiation. Billions of years of damage to our DNA, the blueprint of life, has forced organisms to adapt powerful repair mechanisms to cope with this damage. Repair isn't a special event. It is a daily occurrence. The cells in a single drop of water undergo mutations every day as they swim about, dividing and evolving. Many, if not most of these mutations will prove devastating to the cell, if not wholly lethal. In some cases, the cells will detect and repair the damage. In rare cases, the damage will result in a stable mutation which, in the rarest of cases, may even prove beneficial. Given time, such a rare mutation may result in a minor evolution of the species. Though these events are incredibly rare, most cell damage will either result in repair or death to the cell. In most cases, a cell can either repair damage or will automatically self-destruct if it cannot. In some rare cases, the cell can be damaged in a way that does not trigger a self-destruct but causes the cell to grow out of control, becoming cancerous. Our bodies cannot detect the rogue cell from normal cells. This is how cancer is formed. When we are exposed to ionizing radiation, be it man-made or natural, the damage to our cells and DNA will result. The important thing to understand is that DNA damage is a normal part of our everyday life, and the damage caused from man-made radioactive materials not different from damage from other natural sources of ionizing radiation, at least in how it affects our DNA. If this is true, if we have such well-constructed mechanisms for recovering from damage from ionizing radiation, why then is ionizing radiation considered dangerous? And what are the risks? Why do I not fear the natural uranium in the ground or the potassium in my body, for example? To understand this, we must first understand the two major factors which change our exposure to radiation. Intensity, the amount of radiation you encounter per second, and energy, how powerful each particle of radiation is. When radiation is emitted from a source, the energy of the emitted particle is very important. Low energy particles interact differently with matter than do higher energy particles. Very high energy particles can literally blow entire pieces of your DNA apart, causing double-strand breakages and other hard-to-repair events. Lower energy particles may cause more single-strand breakages, sometimes causing less damage. When radiation is emitted from a source, the amount emitted must fill a greater and greater amount of space as it travels away from the source. This same effect can be seen when moving your hand away from a light in the dark. The intensity of the light against your hand reduces. This is because the number of photons of light emitted from the bulb are constant, but the number striking your hand decreases as your distance increases. If you are near something radioactive, the act of moving away from the object will reduce the number of particles impacting you, and therefore reduce your exposure. Just like the light, the numbers of particles emitted is steady, but the space they must fill grows as they move away from the source. Now, consider this chart. At the source, the radiation is at its maximum, perhaps 100 photons, we'll just say, in all directions per second. As an example, holding this object exposes your hand to 100 photons per second. As we move away, the same photons fill a larger and larger area. Now your hand, which is the same size, is hit by fewer and fewer photons as it moves away. At the third distance from the source, your hand is exposed to less than 1 photon per second. Intensity is changed by distance, but also by the sheer number of energetic particles emitted from a source every second. You can start with a weaker source as well. Consider this table. What do you see? A wooden table, a rock, a banana, and a small radioactive sample disk. What if we could see these objects based on their radioactive intensity and not using normal light? Let's cut the light off and see. These objects glow with an intensity proportionate to their radioactivity. The table faintly glows of natural radioactive material found in all wood. The banana is also slightly radioactive. The potassium in the banana undergoes about 14 radioactive decays per second. The rock contains some uranium and glows from this. If a radiation detector, such as a Geiger counter, were placed near the rock, it would register a slight increase of radiation. This small radioactive sample disk glows quite brightly. The little disk undergoes 37,000 radioactive decays per second. Let's cut the light back on. Each of these objects exposes you to radiation and carries a cancer risk. Yes, even the banana and the table. Risk is always present. But how much? The risk from exposure to ionizing radiation increases with respect to dose in a linear fashion. This means that exposures which are relatively small will result in a risk which is relatively small, while exposures which are relatively high will result in risks which are relatively high. While the effects on DNA are reasonably understood for higher doses of radiation, there is some debate over the effects of low doses. The BEIR-7 report issued by the National Academies is perhaps the most qualified document to date on this subject. The BEIR-7 report supports a model for predicting change in risk with respect to change in dose. This model is known as the linear no-threshold or non-threshold model. In this model, there is believed to be no safe level of radiation where risk is zero. As dose changes, so does risk. Low doses, which the BEIR-7 report considers to be under 100 millisieverts, becomes hard to pin down. To illustrate, suppose you follow the life of 100 people of random sex, age, etc. If each were exposed to one dose of 100 millisieverts, the BEIR-7 report indicates that one of these people will die of cancer induced from this dosage. But this is only 1 out of 43 who will die from cancer from all causes. The other 42 people who died from cancer did so from other sources, such as smoking. This makes valid radiation-induced cancer for low levels of radiation hard to pinpoint. Using this relationship, it would be possible to suppose that one dose of 1 microsievert might carry a lifelong risk of fatal cancer of approximately 1 in 10 million. Of course, such an estimate is very much an approximation, and determining the real dose and risk require years of work as a qualified health physicist, though this guess may not be terribly far off. Understanding risk, we must also recognize that there are various pathways in which we may be exposed, and not all of these pathways are equal. External exposure is often partially blocked by our skin and tissues, and commonly very short-term, such as holding a uranium sample in a classroom. By contrast, internal exposure is often long-term, such as inhaling or ingesting a radioactive dust particle from that same uranium sample. Radiation is most dangerous to organisms when the source is internal, such as ingestion or inhalation of radioactive material. This is because the dust or other particulate radioactive material may be caught near the fragile and ultra-thin tissues inside of our bodies. The intensity at such close range can be very great, and the time required for our bodies to expel this material can be hours to as much as decades. This is why holding a uranium sample carries very little risk, but you should always wash your hands and wear a mask. Fear of radiation is often born out of a lack of understanding of the nature of radiation. Radiation carries a risk which increases as the dose received increases. This has been established by science. Radiation carries a risk of cancer and other genetic diseases. In fact, radiation can prove acutely fatal if the dose is very great. But radiation is also around us all of the time. Radiation must be understood and not feared based on a lack of understanding. We must not fear to hold a uranium sample in a class or receive an X-ray at the dentist. On the other hand, we must take seriously accidents involving radiation and question the sources of exposure which have little if any benefit. Above all, we must use science and think critically.